Right, thank you, Dries. So, hello everyone. My name is Milan, and together with my colleague Jon, we will talk about in this Tech at Lunch session about cross-domain knowledge modeling and simulation. So, as Dries already said, the cameras and microphones of yours are muted during the presentations. Questions can be asked by raising your hand or putting them in the Q&A chat, and we will record this event and share it at a later moment. So first of all, we will give you a motivation and an introduction why we actually need cross-domain knowledge modeling. So if we look at the tendencies of new Mechatronic products that we develop, we can actually see that these become more and more complex because we want them to perform more and more functionalities. Think, for example, about your car. In the beginning, cars had basically one functionality, and that's to bring people from point one to point B. But over the years, cars have gotten increased functionalities like adaptive cruise control, but also like lane keeping assist, GPS systems, and so forth. And now we even want them to make fully autonomous. So this all comes with a rising complexity, which also introduces new challenges to design them. Because of this increasing complexity, we need more specialized engineering disciplines that all work together in order to obtain the full system. So why do we need? So what we typically see is that these specialized engineering disciplines or teams that work in different companies, other countries, and so forth. So, for example, we have a mechanical design team responsible for the mechanical design of the system. We have a control design team, an embedded design team, and so forth. And they usually work in parallel as to on their own part of the design. However, this comes with some problems. This comes with some problems as we often don't know how these different designs impact each other. For example, if a mechanical engineer changes something in their design, it might have an impact on the control or embedded engineers. And if it is not communicated correctly, this might result in integration errors, redesigns, suboptimal designs, and so forth, which is, of course, not wanted. So therefore, it would be handy to try and keep all these dependencies together, or these different disciplines, while still maintaining a divide and conquer strategy to enable better collaboration by means of a cross-domain knowledge model. So to give an example, we have a design of a system, and each engineering discipline, like for example, electrical, mechanical, software, and so forth, choose their own components or are responsible for designing their own components of the system. But they all have a certain influence onto each other, which is either implicit knowledge, from which they also think like, okay, I don't need to communicate this to other teams because it's not relevant for them because they don't know, or they might even not know that their domain-specific design influences these other engineering disciplines' own design. So therefore, we created a tool called Modest, which stands for Mechatronic's ontology co-design tool. And what it does is that you can formalize these different dependencies in a so-called model. And what you can use for this is the modeling part of Modest, which is created in Eclipse. And it consists of two layers, which we derived from the classical approaches. So first of all, you have a top layer which contains information about KPIs of the system and architectural related KPIs or requirements. And then a second layer has more detailed information about the system and the design, about its composition and the system performance. And these two can then be linked to each other. When you then have developed such a model or formalized all this information in such a model, you get this knowledge model, which can then be imported into the reasoning tool of Modest, created in Python. This is a graphical user interface tool, and you can reason about this or on this knowledge to obtain new information. So also to mention, this Eclipse application is made with a graphical user interface, as we will see later on. So you can just drag and drop with some boxes. So now let's see how we can design a system and use such a cross-domain knowledge model to support it. So if you want to design a new system, you of course have to think about, first of all, think about what you are going to design and also why do we design the system. So what functionalities does it have to perform? What do the customers ask us to the system to be able to do, and so forth. And yeah, this is typically also called requirements. So for example, let's say we want to develop a drone for a certain mission. So what and why a drone and for the certain mission. We come up with some requirements like hover at a certain altitude, have a certain error, fly for 15 minutes with a battery state of charge of 10%, be able to carry a certain payload, and so forth. But if you think a little bit further about these requirements, you can already see, like, for example, this 15-minute flight time, that it's not that straightforward to just give at one team or one discipline and say, like, okay, you're responsible for this requirement, because the flight time of a drone is, of course, dependent on a lot of parameters, all belonging to different types of engineering disciplines like power usage, the weight, and so forth. So that's why we want to why you want to formalize these dependencies to get a better and optimal design with less integration errors. So if you want to put this into the Modest tool, you first model these at the property ontology, because what we usually see is that formalizing these KPIs is usually done on whiteboards, or it's implicitly known, or in Excel sheets and so forth, which is distributed everywhere. So what you can do is really model them explicit in Modest at this first level in the modeling, the KPIs in architecture. And you can model these as properties, and these can be either derived from requirements, which are then at the requirements level, or knowledge and architecture. So taking a deeper look at this, you have these requirements-based properties, which we directly derived from the requirements mentioned before, like the flight time that we wanted to obtain, the takeoff time, a certain acceleration, the payload, and so forth. So what these say is, we ask ourselves, like, okay, does the system fulfill this property? So does it also fulfill this requirement? And if so, we can answer yes to a certain property. So these are questions which can be answered by yes or no. And these are also connected with a requires relationship. Like, okay, we have, for example, here a top level property called valid system, which means, okay, our system really conforms to the requirements that you have mentioned. And this requires then that it fulfills this property, this property, this property, and so forth. Okay, so after then reasoning on requirements, you can brainstorm meetings and so forth, or reason on your own design how you are going to develop the system. So come up with some conceptual designs. And these also have properties, but then at architectural level. So this information can also be modeled in at the KPIs and architectural level in the property ontology. And here we refine the requirements level on properties. Like, okay, if we think about carry enough payload, what does this mean? Okay, this means that the system or the drone itself needs to have enough thrust. So you can say, okay, we need to have enough thrust. And what does this mean? You can refine it like, okay, you need a good thrust to weight ratio, powerful motors, and so forth. And these then can be our more refined properties at an architectural level that you can then evaluate, as we will see later on. So when continuing with your design, looking at the classical approach, typically it is the system itself is divided into components that are all connected to each other, and there are already tools available for this, like SysML or Capella. And you can eventually come up with a certain system decomposition and system architecture that defines like, okay, we have these components, they're connected to each other with these kind of interfaces and so forth. However, yeah, besides how things are connected, this does not state how the performance of each component influences another component, possibly assigned to another engineering domain, of course. So what you can do then with the Modest tool is also use this as an input to make the next level of the modeling of the model, which is the decomposition and performance at decomposition and performance level, where you can model these performance influences and so forth. So this is an example. So we will take a further look at these top things. So what you can see is that we have two boxes here, and each box represents a certain engineering domain. So now we have electrical and mechanical. And what's inside each box is what these specific disciplines or teams are responsible for, and what they also think about, or how they are going to evaluate their own domain-specific design. So what we can see is that electrical engineers are, in this case, responsible for choosing a battery and a motor as a component. And these components have certain design parameters, which are the tuning knobs. So if you choose a new battery, these parameters can change, which have then an influence on certain performance values, which are measurements or measures of the performance of your system. Like, for example, what is the total power consumption? What is the max thrust that the drone can deliver, and so forth. And these parameters can then be connected to each other across domains, such that you can see, okay, if I change something in my own domain, how are you going to influence other domains? And do I need to talk about this to them? Like, okay, I will change this, so you also need to know about this, because otherwise we might have an integration error or suboptimal design, and so forth. So also, as you can see, these are all boxes and lines between each other. So it's just drag and drop and putting lines between it. So it's fairly easy to make. So now what we have discussed is that that there are two different layers. And so the KPIs and architecture and decomposition and performance. So you can also connect these two with each other to really close the gap. And this is done with a satisfies relation that can be seen here. And what this actually means is that you trace back the performance to a certain property. So, for example, you have a property good trust to weight ratio. You also want to really evaluate if that's actually the case. So you have a performance value trust to weight ratio and a certain evaluation function. And after a certain test or simulation, you can say, okay, our trust to weight ratio is 4, for example. You evaluate it like, okay, trust to weight ratio is 4, so it's indeed bigger or equal than 2. So we can say that our good trust to weight ratio is indeed satisfied. And this is so in this way, you can really trace back system performance measures to your properties and also the requirements. So after then setting up such a model, you can also then reason on it with the Modest reasoning tool that is also included with Modest, and it looks like this. So one of the main parameters. So I will discuss now one of the main features of it. So first of all, you can derive domain influences. So what it does is look like, okay, where do we cross boundaries between domains? Such that okay, I am an electrical engineering discipline. Which other domains do I influence? And also, how do I influence them, or with which parameters, such that I know about this. You can also see for a certain variable, okay, I'm going to change this variable. Which other variables does it influence, and how? And then, okay, I will change this, so I need to talk to someone that I influence about this, if it will affect their design, or do some analysis if this affects their design. You can also do some trade-offs, like, okay, you know, for example, you can put plus and or minus signs on these influence relations, which means, okay, if we change another variable, for example, increases clock frequency variable, then if it's a minus sign, this performance variable will decrease, and if it's a plus sign, if you increase, then the other side also increases. So with the trade-offs, you can see if changing a certain design parameter has both a wanted and unwanted effect. Like, okay, if we change clock frequency, it will have an impact on the worst case response time and on the cost. So in any way, if we change it, it will both have a wanted and unwanted effect. So this can be given to the engineers as some information, like, okay, you will have to do some trade-off analysis right here to see what is most suited for your design. And lastly, one of the main functions is generate engineering contracts, for which we will see, okay, how does one parameter influence other parameters, or where do we cross the boundaries? And what you get are these assumption guarantee contracts between two domains. So you have a set of assumptions, which means, like, okay, you can assume values from these performance values from another domain. So the electrical domain can assume that the trust to weight ratio will be bigger than 2 from the mechanical domain, and the mechanical domain can assume from the electrical domain that the motor mass will be 250 grams, the battery mass will be either 300 or 600 grams, with which they then can continue to develop their own design. But they also have to, of course, guarantee some parameters. So the electrical design also has to guarantee that the motor mass is, of course, these 250 grams. Otherwise, you will have integration errors, of course.
Yes. So I'll briefly talk a bit about the co-simulation aspect. So the cross-domain knowledge model that Milan showed previously, it shows this relationship between design parameters and performance values, but it's mostly qualitative. The actual values for these performance values often actually come from domain-specific models, analyses, and things like that to actually get the quantitative information. An issue with this, especially with the design of these advanced cyber-physical systems, is that the different engineering domains often have their domain-specific tools. But for some of these analyses, we often need to co-simulate multiple of these models. For example, you might need to simulate a model of your drivetrain together with a model of your drivetrain from AIM-Sim together with the controller modeled in MATLAB Simulink, for example. Now, we can set up these co-simulations manually, but that takes quite some manual effort. It can be error-prone if you're working with the wrong values, for example, and it can also lead to inconsistencies if you're working with wrong design parameters, for example. So basically, the approach that we are taking is we're using this cross-domain knowledge model as a source of truth to basically configure and correctly set up our co-simulations. And then once we've actually run these co-simulations, the results of these we can actually feed back to the cross-domain knowledge model as these, for example, these performance values to actually check then, for example, these satisfies relationships. So we actually feed back the results of our analysis to the cross-domain knowledge model to keep this also updated. To give a bit more detailed look at how this actually works, we have basically, again, two tools. One is the co-simulation modeling tool at the top here, which I'll show a bit more detailed in a minute. And then we have this co-simulation execution tool to actually run these co-simulations. So for example, in this co-simulation modeling tool, we actually basically import the cross-domain knowledge model, and also we can import models from different modeling tools. In this case, we're working with functional mockup units, so we're actually using the FMI standard to import these models. So the co-simulation modeling tool looks somewhat like this. So at the bottom here, you see our cross-domain knowledge model instance. At the top here, we have our imported FMUs, our imported models. We then have defined multi-models where actually you take these different FMUs and couple them together into a big model, basically. And then we have test scenarios that we can define. So basically, that's our modeling tool, and then we have this configuration that comes out of it. So I mentioned these test scenarios. This is an illustration of what these test scenarios are. Basically, you can define different tests, different analyses with different analysis steps. For example, these steps could be running co-simulations. It could be running scripts, for example, for post-processing or pre-processing, or also just for standalone analyses. They can have input and output artifacts like just values, for example, but also traces. So like this throttle ramp trace input and this thrust curve, but also these values, like for example, we have this input value mass, for example, and this results, this maximum thrust and the thrust to weight ratio, they're then actually linked specifically to design parameters or performance values in the cross-domain knowledge model, which is illustrated with these arrows here. The next to this, we have this execution tool that actually can take this model, this co-simulation model, and actually then run these test scenarios. So to actually automatically determine in which order these different steps, these different analyses need to run. It will actually look at the dependencies. For example, if a certain parameter has to come from the cross-domain knowledge model, it will fetch it from the cross-domain knowledge model. It will run these analysis steps. And then, for example, the outputs, like for example, this rise time here comes out of the analysis. It's linked to cross-domain parameter performance value in the cross-domain knowledge model. So the output, the result of this analysis, will actually be automatically fed back to our cross-domain knowledge model. So basically, in this way, we can ensure consistency because we have these links specifically to the cross-domain knowledge model, where we're using cross-domain knowledge model basically as a single source of truth. Another advantage of this approach is that basically domain experts can set up these co-simulations, they can set up these test scenarios, and then after that, once they're set up, basically anyone can actually run them to check what, for example, their design changes. And this is actually also a first step towards continuous validation. So in the rest of the project, we actually want to look at using these test scenarios in a continuous validation scheme, where if an engineer changed something, the design parameter, for example, in the cross-domain knowledge model, we actually automatically rerun the required simulations to check if our design is still correct or is still valid.
All right. So to conclude this Tech at Lunch session, we have seen the models tool, which engineers can use to keep track of dependencies between different engineering domains for a certain design. And this can be done by modeling indirect links or like links between domains, which result in indirect links that can support the design process and eventually, hopefully, reduce the integration errors. And it can also be used to generate engineering contracts to enable co-design process and so forth. And we've also seen that a more practical use case of it is that it can support the cross-domain co-simulation by using these kinds of models to maintain consistency in co-simulation, and also to do some continuous validation, optimization across different domains, and so forth.